Dr. Knack.
Dr. Bilo.
I can already see University of Lucerne, architecture and building technology. What do we do today?
Switzerland. We're going to visit Professor Dr. Andreas Lübli. He holds a PhD, I think it was structural use of glass at that time. He worked long times in industry as a facade consultant, engineer, did build nice buildings, and now is since quite a while a professor at Lucerne, doing the facade program and having a super nice test rig. That's why we are here.
I've heard it's actually Europe's biggest facade test rig.
Yeah, well, I think it's one of the biggest.
Okay.
The size is enormous, you're going to see it. And we're going to talk about tolerances, movement, and of course his test rig.
No, interesting. Let's go. I think I can already I can already see him. He seems to be parking the place over there. Hi.
So, Andreas, today we talk first about tolerances. Why tolerances? How do we deal with it? What are the design principles? The second one is about movement. And then the third one, which is why we are in Lucerne, the test rig. I start with tolerances. Why? How do we deal design principles? So, why tolerances?
Tolerance, they exist because you have the facade in front and behind you have the main building structure. And there are also always differences between the structure and the envelope. And these differences, geometrical differences, they have to be compensated by the brackets. And the brackets have to take these tolerances. And here we have some examples of these brackets. These are the connections between the building structure.
Building structure comes from here.
So the building structure comes from here. Here, this part of the bracket is fixed to the building structure, to the main structure. And here you have the piece where the facade element finally is then
so
fixed.
So facade element is kind of hooked in here.
It's hooked in here, yeah. And this element here is very important because it has to take the tolerance in 3 directions. So in vertical directions, in horizontal direction, this way, and also in this direction.
Okay. One direction is this one. This screw goes up and down.
This goes up and down. This can be adjusted vertically.
This is a horizontal one with these long bowl holes. This one.
This holes here, yeah, and then you also have here the possibility to slide here.
I can hook it in here and then move it in this way. Okay. And then there's the third direction, which is this one.
This one, yeah.
Okay. And then with all 3 dimensions, I'm able to position the facade in a, say, accurate position versus a main structure which may be having more tolerance. So, why? Because we have different construction parts which are connected. Aluminium is very precise versus the main structure which is less precise.
Exactly, yeah. The main structure is steel construction or is a concrete structure with tolerances between plus minus 10 millimeter. And you come with an aluminium construction which has tolerances between 1 and 2 millimeters. And this has to be compensated.
This has to be compensated. This is the why. Then how to deal with, that's what we just saw in the sample. And the design principle?
The design principle, actually, you have to design these elements according the tolerances you have on the building. So you really have to think about the structure. You have to think about how much deviates the structure from the theoretical levels.
Oh, that's movement. That's what we do in a minute.
No. This is tolerances, because you have to know how much can the structure deviate from the theoretical position where you want to fix the facade. And this also gives you the dimension you have to have here in this bracket. So the adjustable movement, you can, or not movement, but
so the dimension of the possible tolerances of the concrete versus the aluminium.
Exactly,
that's
this
3 centimeters something.
Exactly, yeah. So if you have a 10 millimeter deviation from the concrete structure and another 5 millimeter from steel structure behind, this makes plus minus 50 millimeters, and this gives you finally the dimension here you have to take with this tolerance.
Okay, so tolerances between main structure and facade, that's, say, the design principle. Let's go to movement. Why do we have movement and how do we deal with movement in facades?
Why do we have movement? So structures, they move. They have to take loads, and when they take loads, for example, wind loads, they move to the side. So they are not stiff structures, and these movements they have to be taken, or these movements are also transferred to the facade. But the facade has to be independent from the structures to allow these movements. Otherwise, you have very high forces in the brackets in the construction, and this will destroy finally your facade.
Okay, let's take the bracket again. So the bracket is now fixed correctly at position, and then the facade is hooked into it at a certain point. And if there's, say, some horizontal movement, it could actually move, slide in this situation.
This part can actually move on this bar here. There's another component which is thermal movement, so the facade will heat up to 60-70 degrees. That creates plus minus 5 millimeter of elongation of these elements, and this,
which is then the outside versus the inside,
exactly,
standing with 20 degree, no changes.
Exactly, yeah. And you have to allow for these movements in the facade joints. And depending on the facade system, finally you have either you take this in these parts here, or if you have a curtain wall, a classical curtain wall with facade elements, you have these gaps, these joints, where you finally take the movements.
Then that takes a movement. So design principle, we have to identify how much movement we do have, and then we have to design according to this.
Exactly, exactly. So you know the length of your profiles, you know more or less the temperature they have in winter and in summertime. This gives you the thermal movement. Then you know the movement of the building. This is information you get from the structural engineer, so he can tell you how much the building will incline, or the floors will be deflect due to a traffic load, for example. And this has to be then calculated, and the movement joints have to be designed according these requirements.
Okay. Let's go to the final sticker for today, testing. This is your test rig. What are the, say, parameters you test, and what type of testing are known? And explain the test rig.
You have to test every facade. Every facade system has to be tested, and there are three things you have to test. First is the air tightness, the water tightness, and the structural safety. And these three tests will be carried out on this test rig. And air tightness, for example, is very important for the energy performance of a building. So if you have a too high air leakage, you lose a lot of energy, and this is not allowed and not wanted. So the facade has to be airtight up to a certain level. This depends also on the wind load, which is applied then on the facade. And of course, the facade has to be watertight. And the last test is the structural safety test. So here you can test the facade up to the highest wind loads, the wind pressure, so that the facade can resist this wind loads. The principle behind this is very simple. So you have a closed chamber, airtight chamber, and in front of this chamber you have a big opening you can see here. So the opening here is 8 meter large and 12 meter height. So in theory can install.
That's a big opening.
Yeah, it's one of the biggest facade test rigs actually in Europe, and we can install a facade up to these sizes, and we installed it on the open part of this closed chamber, and it's a very simple principle behind it. We just put some air in this closed chamber then and blow it up. Or we take the air out and we create some under pressure. And at the same time we measure the air which is going through the facade.
Okay.
So this is actually
This is airtight.
This is airtightness.
And now water.
And water. This is done by a spray bar system, which can be seen here. So we have installed this in front of this facade. We are creating something like an artificial rain. It's a very heavy rain. We can create here, it's 1.5 liter per square meter per minute, which is sprayed on the facade, and at the same time we create an under pressure inside this test rig. So we really try to suck in the water and to test all the joints and all the critical parts of the facade.
Okay. And now when I look at this, it's perfectly sealed, it's perfectly say, connected to the main structure. You take the microphone and I may peel off and we see what.
No. Don't touch it. So this is for a client. We are doing testing and it's not finished the test. So this is a continuous test. We just
Okay, I'm not allowed to destroy.
No.
Okay, thank you. Well, then I'm not allowed to destroy anything, which is sad.
He always tries to peel something off or actually destroy something. But I'd like to know, can we actually let it rain? Can you set on the water sprayers?
Unfortunately, I cannot switch on the rain bar system because this is an ongoing test. So the client was here yesterday and he has to come again on Monday. So the tests we are doing here are actually, we are a notified body in Europe. So our tests, they are accepted in the whole Europe and it's a quite official thing. So,
So
it's also sometimes
right now
it's very
the
secret
sensor
what
is
we're doing.
inside run and we are not able to manipulate anything. So
If I
right
peel
now it
off
doesn't
something
rain.
here, he has trouble.
Yeah, exactly. So
We don't
take
do
your
that.
fingers off.
We don't do that.
Thanks.